morning, everyone. I am Dr. Tesi, Assistant Professor, ABES Engineering College, Ghaziabad. My today topic is maxima and minima of function of two variable. In the first part, we discuss how to find maxima and minima of function of two variable. In this video, we discuss application of maxima and minima. So first of all, we recall the method to find maxima and minima. So if RT minus S square is greater than 0, then and R is less than 0, then the function fxy is maximum at the point AB. If RT minus S square is greater than 0 and R is greater than 0, then fxy is minimum at AB. And if RT minus S square is less than 0, then the function neither maxima or nor minima. Such point is called the saddle point. Similarly, if RT minus S square equals to 0 at AB, then further investigation is required. So this is the process to finding maxima and minima. Now we take one example. So a rectangular box opened at the top is to have the given capacity. So find the dimensions of the box requiring the least material for its construction. So it is a rectangular box. So let x, y, z be the dimensions of box. X, Y, Z be the length, width, and height of a rectangular box. Then its volume V equals to X, Y, Z. Since capacity is given, that is volume is given. So V is given. Now we find Z in terms of X and Y. Now we find the dimensions of box requiring the least material. So if we minimize the surface area, then the dimension become least, and so the least material will be required for its construction. So since the box is open, so we take the surface area xy plus 2yz plus 2zx. Now we change it to two variable x and y. So we put the value of z, that is v upon xy plus 2 v upon xy. Then we get xy plus 2b upon x plus 2b upon y. We cancel y and x. So we get s in terms of x and y. Let us take a function f of xy. Now for stationary point, we have to find del f over del y. So del f over del y is y minus 2b upon x square, and del f over, sorry, it is del f over del x. Now we find del f over del y. It is x minus 2b upon y square. So it is equation 1 and it is equation number 2. Now we find r. So r is del square f over del x square, which is 4v upon xu. We differentiate del f over del x again in terms of x. Similarly, we find s del square f over del x del y. It is 1, and t equals to del square f over del y square, and it is 4b upon y cube. Since x is constant, so x becomes 0, and it is minus 2 upon y cube, then it is 4b upon y cube. Now for stationary point, We put del f over del x equals to 0 and del f over del y equals to 0. Then we get the two equations. One is y minus 2b upon x square equals to 0. This is 1. And x minus 2b upon y square equals to 0. This is equation number 2. Now from equation number 1, we get y equals to 2b upon x square, and put in equation number 2, then we get x minus 2b into x4 upon 4b square equals to 0. So this implies x1 minus x cube upon 2b equals to 0. Since x cannot be 0, it is the length. So we get x equals to 2b to the power 1 by 3. Now, using equation number 1, we can find y. So y equals to 2b upon x square. So it is 2b upon 2b to the power 2 by 3, and it becomes 2b to the power 1 by 3. So we get x and y. It is the stationary point. So it is stationary point. Stationary point. X and y, 2b to the power 1 by 3. Now at this point, we calculate r. So r is 4b upon 2b equals to 2, which is greater than 0, and s equals to 1. Similarly, we calculate t. So t equals to 4b upon 2b equals to 2. Now we calculate rt minus s square. That is 4 minus 1 equals to 3, which is greater than 0. And r is also greater than 0. So s is minimum when x equals to y equals to 2b to the power 1 by 3. So surface area is minimum when x and y equals to 2b to the power 1 by 3. Now we calculate z. So z equals to b upon xy. So v upon 2b to the power 2 by 3, and it is 2b to the power 1 by 3 by 2, or it is y by 2. So we find x, y, and z. It is the dimension of a rectangular box. Now, in the next question, find the shortest distance between the lines, two lines. So we can find shortest distance between the two lines. So let PV any point, let PV any point on given line 1. So we take PV any point on line 1, that is x minus 3 upon 1 equals to y minus 5 upon minus 2 equals to z minus 7 upon 1. We take as lambda, say. Similarly, let q be any point, q be any point on line 2, that is x plus 1 upon 7 equals to y plus 1 upon minus 6 equals to z plus 1 upon 1, and we take mu, say. So we find 2 point P, that is P is lambda plus 3, 5 minus 2 lambda, and 7 plus lambda. And from line 2, we get the point Q, which is 7 mu minus 1 minus 6 mu minus 1 and mu minus 1. These are the 2 points on these two lines. Now, distance between 2 points PQ, let us take D. So, distance between these 2 points P and Q becomes lambda plus 3 minus 7 mu plus 1 whole square plus 5 minus 2 lambda plus 6 mu plus 1 whole square plus 7 plus lambda minus mu plus 1 whole square. So we apply distance formula, that is x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So it is the distance, and it becomes 6 lambda square plus 86 mu square minus 40 lambda mu plus 116. Now, since distance is maxima or minima, so its square will be the maxima or minima. So we take d square equals to 6 lambda square plus 86 mu square minus 40 lambda mu plus 116, and we take is function of lambda and mu. Now, for maxima, minima, or for stationary point, we can find the first order partial derivative, that is del f over del lambda. It is 12 lambda minus 40 mu. We differentiate f with respect to lambda, and we find del f over del mu, which is 172 mu minus 40 lambda. And for stationary point, we put del f over del lambda equals to 0 and del f over del mu equals to 0. So we get two equations, 12 lambda minus 40 mu equals to 0 and 172 mu minus 40 lambda equals to 0. This is equation 1 and this is equation number 2. If we solve equation 1 and 2, so we get lambda equals to 0 and mu equals to 0. So 0, 0 is the stationary point. So 0, 0 is the stationary point. Now we calculate R, S, and T. So R equals to del square F over del lambda square. We differentiate del F over del lambda again with respect to lambda. So we get 12 and calculate S, that is del square F over del lambda del mu. We differentiate del F over del mu again with respect to lambda. So we get minus 40. Similarly, we calculate T, that is del square F over del y square, which is 172. Now calculate RT minus S square. So R is 12, T 172 minus 40 whole square. If we calculate this, it is greater than 0. And R is 12, which is also greater than 0. So we say the shortest distance at point 0, 0, d equals to root 116. Since lambda and mu is 0, so all the term is 0. We get only root 116. It is 2 root 29. So it is the shortest distance between the 2 points. So this is all about the maxima minima. So now thank you so much. These are some references.